Hello, 8th graders, and welcome to Math Weekly number 7. In this Math Weekly, our focus skill will be on evaluating square and cube roots. Today we are going to review how to evaluate and estimate square and cube roots. Remember, there are three types that we're going to look at: perfect square roots, perfect cubed roots, non-perfect square and non-perfect square roots. The first two, we are going to evaluate what they equal because they are rational numbers. Rational numbers are numbers that terminate as a decimal, so we will see that these are whole numbers. The non-perfect square roots that we will look at, we will need to estimate because they are irrational. Because we're using paper pencil estimation strategies, it is important for you to check with a calculator when you have one to make sure that your estimate is accurate, especially if you are comparing non-perfect square roots and they come to a very close estimate. So, evaluating perfect and perfect square roots and perfect cube roots. We can generate a list of the first 12 perfect square roots, and if we can generate this list, it shows us how to calculate any perfect square root. So to figure out what square root equals 1, multiply 1 times 1, which is 1. So the square root of 1 is equal to 1. To figure out which one equals 2, do 2 times 2, which is 4. So the square root of 4 equals 2. 3 times 3 is 9. So the square root of 9 is 3. 4 times 4 is 16. So the square root of 16 is 4. 5 times 5 is 25. So the square root of 25 is 5. 6 times 6 is 36, so square root of 36 is 6. 7 times 7 is 49, so square root of 49 is 7. 8 times 8 is 64, so square root of 64 is 8. 9 times 9 is 81, so square root of 81 is 9. 10 times 10 is 100, so the square root of 100 is equal to 10. 11 times 11 is 121, so the square root of 121 is 11. And 12 times 12 is 144, so the square root of 144 is 12. This list will also help us estimate the non-perfect square roots because they will be in between these perfect square roots. Our perfect cube roots can be generated using a similar process, except to multiply the number 3 times in a row. So 1 times 1 is 1, times 1 more is 1. So the cubed root, and notice there's an index of 3, the cubed root of 1 is 1. 2 times 2 is 4, times 2 is 8, so the cubed root of 8 is 2. 3 times 3 is 9, times 3 is 27, so the cubed root of 27 is 3. 4 times 4 is 16, times 4 is 64, so the cubed root of 64 is 4. 5 times 5 is 25, times 5 is 125, so the cubed root of 125 is 5. And 6 times 6 is 36, times 6 more is 216, so the cubed root of 216 is 6. And if you needed to extend this list further, you would just need to continue multiplying the whole number 3 times in a row. Now, let's talk about how to estimate non-perfect square roots. To estimate a non-perfect square root, first determine what two perfect square roots and whole numbers the non-perfect square root is between. This tells the whole number of the non-perfect square root. Second, write the portion of the distance between the first perfect square root and the non-perfect square root, and the distance between the two perfect square roots as a fraction. Third, divide the fraction to convert the non-perfect square root to a decimal and round appropriately. So let's look at an example. The square root of 60 is a non-perfect square root. It is between the square root of 49, which is 7, and the square root of 64, which is 8. This was step 1, determining what two perfect square roots and whole numbers the non-perfect square root is between, so that we know what whole number value this square root has. The next step is to create a fraction. The numerator will be the distance between the first perfect square root and the non-perfect square root, which is 11, and the two perfect square roots, which is 15. So we know that this is equal to about 7 and 11/15. So we divide 11 by 15. We need two decimal places so we can round it to the nearest tenth. 15 will go into 110. 7 times. 7 times 5 is 35. 7 times 1 is 7, and 3 more makes 10. So there's 5 left over. Bring down our 0. 15 goes into 50 3 times, which is 45. So we have 5 left over. Bring our decimal straight up, and the 3 keeps the 7 the same. So it gets the whole number 7 and the decimal 7. So the square root of 60 is equal to 7.7. Now let me show you the square root of 60 on a calculator. The square root of 60 on a calculator is 7.74, which shows that our estimation strategy is pretty close. It rounds to the same tenth. Let's look at another example. Okay, in this example we want to take the square root of pi. Remember, pi is 3.14, so we need to figure out what the square root of 3.14 is between. What's between the square root of 1, which is 1, and the square root of 4, which is 2. So the square root of 3.14 must be 1 point something. We need a fraction to show the distance between our first perfect square root and our non-perfect square root, which is 2.14. So 2.14 goes in the numerator, and 1 and 4, which is 3. Now we need to divide this. 2.14 goes inside, 3 on the outside. 3 goes into 21 7 times, which is 21, and goes into 4 once, which is 3. The 3 keeps the 7 the same, so we get that the square root of pi is equal to 1.7. Now let's try it on the calculator and see how close this estimation strategy is. So 3.14 square rooted 1.77. So theirs rounds to 1.8. Ours is at 1.7, but that is pretty close for using an estimation strategy for an non-perfect square root. Remember, this is an irrational number. It goes on forever. So we have to do our best to estimate. But this is also why, if you have a calculator available, so for example, after the first few on your PSSA, use it to make sure that your estimation strategy is close enough. So let's look at a little more complicated problem. This says 2 times the square root of 7. So what this means is we're going to have to figure out the value of the square root of 7, and then this is multiplication, so we're going to have to multiply it by 2. So our first step is to figure out what the square root of 7 is equal to. Well, we know it's between the square root of 4, which is 2, and the square root of 9, which is 3. So it's going to be 2 point something. Our fraction is going to be from here. This is 3 as a distance between our first perfect and our non-perfect. Fifths as between the two perfects. 5 into 3.00. 5 goes into 36 times, which is 30. There's nothing left over, so we don't need to round it. So it's about 2.6. So then we multiply 2 times 2.6. 2 times 6 is 12. 2 times 2 is 4, and 1 more is 5. And put our decimal place in. So this value is about 5.2. Now, remember I said it was about 5.2. Let's see what it equals in the calculator. 7 square rooted, that's 2.64, times 2 is 5.29. So it is almost exactly the same. It just rounds up to 2.3. or 5.3, sorry. Let's look at another example. The square root of 130 is between the square root of 121 and 144. So the square root of 121 is 11, the square root of 144 is 12. So it's going to be 11 and 9/23. Because we're running out of time, I'm going to use this to divide 9/23. 9 divided by 23 is 0.39, so that'd be 0.4. So this is 11.4. Now, our problem was not just the square root of 130, but half of the square root of 130. So if the square root of 130 is 11.4, we need to take half of that. If we take half of a number, we really are dividing it by 2. So if we take 11.4 and divide it by 2, 2 goes in 11 5 times, which is 10. Bring down our 4, and it goes into 14 7 times. So this has a value of 5.7. Let's look on our calculator to see how close our estimate is. 130 square rooted and divided by 2. 5.7. So our estimation strategy is very accurate. The square root of 18 is also a non-perfect square root between 16 and 25. The square root of 16 is 4. The square root of 25 is 5. So this is 4 point something. We get 2/9. 2/9 is a repeating decimal. It'll be 0.222. So this is the same as 4.2. Now, our problem did not just say the square root of 18, but the square root of 18 and then add 3 more. So the square root of 18 is 4.2, and we need to add 3 more wholes. So remember, when you're adding a whole number to a decimal, make sure your whole number goes in the ones column. And if you need to, you can add a 0 in the decimals. 2 plus 0 is 2, 4 plus 3 is 7. So this has a value of 7.2. Let's see how accurate we are. 18 square rooted, 18 square rooted, and then add 3 more, and you can see it's very accurate, still 7.2. Now, you can also determine if inequalities are true or not. We're not going to actually work this problem out, but I'm just going to explain to you the strategy. So your strategy would be to use your estimation strategy to turn this into a decimal, okay? And use your estimation strategy to turn this into a decimal. After you have your decimal, see if the one on the left is less than the one on the right. So, for example, if we already used our estimation strategies, we could check with a calculator the square root of 13 times 8. So we would get about 28.8. And on this side, 30 square rooted and then multiplied by 3.14 would give us 17.2. So is it true that 28.8 is less than 17.2? No. So that means that this original inequality is not true. So let's summarize what we've learned about square and cube roots. Perfect square and cube roots can be evaluated because they equal a whole number. However, non-perfect square roots must be estimated since they are irrational values.